so here we'll talk about how to solve the constant coefficient ODE, and this is the outline. So first I will try to explain what is differential equation, and then I will also talk about what is linear differential equation, what is linear, and what is constant coefficient linear ODE, and then so this is a specific type of differential equation, which is easy to solve and has a systematic way to solve. For some other differential equation, just like a non-linear differential equation, it might not be a analytic solution. So, but for this type of constant coefficient linear ODE, we have a systematic way to solve it. So, so you have to memorize something to really solve it. Just go through step 1, step 2, step 3, then you can just solve the constant coefficient ODE for theoretically any degree of it or any order of it. So actually we'll just solve the homogeneous solution and non-homogeneous solution, or we can call it particular solutions, and then we can add them together so that we have the complete solution to the differential equation. Okay, so first is the definition of the differential equation. So I think in primary school or high school, you should have learned how to solve the algebraic equation. Algebraic equation. Something like, for example, in junior 1 or primary school, you might have known also. For example, 3x plus 2 equals 8. This is very easy, so you can quickly see that x should be 2, so 3 times 2 plus 2 will be 8. Okay, so this is so-called the algebraic equation, because within this equation we have algebraic calculations. For example, we have multiplication here, we have addition here, or maybe we can have a division, subtraction, whatever. So they are something like algebraic equation. Or maybe in high school you may have learned something more difficult. Just say exponential to x is 2. Exponential to x is 2. It's still an algebraic equation, but this thing is non-linear. But actually, hopefully, this one is solvable. It is actually x equals natural log of 2. So rather than that, we can still have something like ax squared plus bx plus c equals 0. This is the so-called quadratic equation. And I suppose you should still remember the formula for it. We minus b plus or minus square root of b squared minus 4ac, and then all over 2a, something like that. Yeah, actually we still need to use it for solving the constant coefficient ODE. But this is another type of algebraic equation. So so we know very well what is algebraic equation. So here we try to explain what is differential equation. So in mathematics, a differential equation is an equation that relates one or more function and their derivatives. So for algebraic equation, the unknown, we have some unknown variable in the algebraic equation. Just say this is x is the unknown variable. So for this equation, we try to solve for this unknown variable x, something like that. This is also try to solve the unknown variable x. And maybe you have also know how to solve something like 3x plus 2y equals 7, and then x plus 3y equals 9. And still you still know how to solve it. You can just eliminate x by multiplying this by 3 and then subtract them. Then you can solve y, and then you plug in the y, and then you can know x. So in this case, you have you have two unknown variables here. So the unknown are just a single number, just a single number for the algebraic equation, or maybe for this one, two numbers for the algebraic equation. But for the differential equation, the unknown is not a variable anymore. The unknown should be a functions, and also it should be related to the derivative of the functions, and we can call it a differential equation. And then the next one is the ordinary differential equation. So rather than ordinary differential equation, we still have something called partial differential equation. This is so-called 常微分方程。This one is 偏微分方程。Okay, so this is partial derivative, partial differential equation. Okay, so I'm not sure whether you have learned the multivariable calculus or not, but yeah, at least you should have known the ordinary differentiation or the ordinary derivative, which is something like dy dx. Suppose you have a y which is a function of x, then you can take the derivative dy dx, which is defined as y, I think y of x, y of x plus delta x minus y of x, and then all over delta x, and then take the limit for the delta x tends to 0. So this is the definition of the ordinary derivative. So for this case, y is just a function of a single variable, of the independent variable, of one independent variable, and then we can take the ordinary differential or the ordinary derivative with respect to this function. But sometimes a function can be multivariable. Just say if we have function, just say r is a function of x and y, or maybe in physics, the E field in x direction might be a function of x and y and z. So it can be a multivariable function. And in that case, if we need to take the derivative, we cannot just write dex x y z dx. We cannot write this. Rather than that, we should use the partial derivative, partial x, something like that. This one is not okay, this one is okay. So we have ordinary derivative and partial derivative. And for ordinary differential equation, we only have the ordinary derivative. So an equation only contains ordinary derivative of one or more dependent variable with respect to a single independent. We may have more than one function, but those functions are just with one independent variable, a single independent variable. Maybe you can have I is the function of time, and then V is also a function of time. The current and the potential are also the function of time, and then maybe you can write something like I of t equals c times dv dt. I hope you still remember this one. Or for the inductor, it is something like V of t is equal to L times di of t dt, something like that. I hope you still remember these two. Actually, we need to use these two in chapter 27 and chapter 31 frequently. And here there are some examples. So you can see this is the derivative, this is the function, this is the independent variable function. So e of x is a function related to the independent variable. So this is related to the dependent function. So here this is the second derivative of y, first derivative of y in the original function equals to 0. And then this is x, xy are function of time, and then take the first derivative with respect to time equals to 2x plus y. All of them are ordinary differential equations. Okay, so next we talk about linear differential equation. So this is just a notation. So for example, we can actually write f of x, something like that, or f of x dx dt, something like that. Just choose to mention that. Or for example, we have f of x, maybe f of x equals to sine of x, something like that. Or for this one, this function is related to the function x and also its first derivative. And here is mentioned that this function is related to x, the first derivative, up to the nth derivative. So on the left side, related to all these terms. Or maybe we can have some constant multiplier, and then maybe we can just add them together or multiply them together. And then on the right side, this function, this is another function g, but this function only related to the independent variable t. Okay, so we can just separate the terms apart. Okay, so here it says an nth order ODE is said to be linear. So for this one, we don't know whether it is linear yet, but if this equation is linear, if the functional, we don't call it function anymore, we call it functional, because it is a function of function, so we call it functional rather than function. In Chinese, we will call it a 泛函 rather than 函数. So if the functional f, capital F, is linear, and star can be written as, so yeah, so it's like this is linear if the functional is linear. So just like saying nothing, but actually it says this one can be written as this form. So you can see x, this is x, so we can see x. The first derivative, you can see it here, and then so on and so forth. The first derivative up to the nth derivative. And then here we don't have this term multiplied together. Just say we don't have a x squared, we don't have a dx dt quantity square, or we don't have x times dx dt. So every term consists of only one term of here. Okay, and then it can be multiplied by another function of time, function of the independent variable. So all these functions a0, a1 up to an are just function of time, and then multiply to it. Then we'll call it linear. And then on the right side is still g of t, nothing special. But yeah, the point here is that we only have x, dx dt up to dn dt for each term. We can't really have something like other nonlinear function involved there. So for example, just can see some example. This is our order of 2. So double prime means d2y dx2, the second derivative. So which means that a2 here is 1, a1 here is minus 2, a0 is 1, and then g of t is 0. So this is of course satisfying this equation. And then for this one, this is the third derivative. We don't try to write prime, and then for the derivative more than 3 order, then we will just use a bracket to show this is the third derivative, rather than this one is the x cubed. This one is x cubed, yeah. And then here, this is x prime, so which means that a1 is 3t. So it's just a function of time, so it's still linear. And then a0 is -5, and then g of t equals exponential to t. Okay, so all these equations are linear ODE, and then here we have some example for the non-linear ODE. So for the first one, this one, we have seen this term in red. So we have negative x times x prime. So we have these two terms, this one and this one multiply together. So they are, it is not linear. It is not linear. And then for this one, for the second one, sine of x is a nonlinear function. Sine of x is a nonlinear function. The only linear function is y equals m times x, are linear. Yeah, not mentioning the plus b, because if it is plus b, then you can just put it to the right side to make it on the left side we only have the term for x up to dn dx, dn x dtn, I mean. Okay, so rather than this type of function, then all the other functions are linear, you can say. And then for this one, the fourth derivative plus the second derivative is 0. So sorry, this is not second derivative. This is x squared. This is x squared. So this is not linear. It's not linear. So for these three equations, the red terms have some nonlinear term there. So it's not linear. Of course, exponential to t is not a linear function, but it is on the right side. We don't really care about the function g of t. We only care about on the left side, only we involving the dependent function. So we just move all the terms for the independent variable to the right side, and then we only care about the left side, whether all the terms for the dependent function to be linear or not. Okay. So far, any questions? Okay. So here, when we talk about linear, then it's well known that it satisfies a property like this. So f is linear means that it should satisfy this equation. This equation means if f is linear, so we have f of this one. So within this one is only related to the independent variable t, and then equals to this one. So you can just feel like we can just separate it, because for this one it is actually two property. One is so-called the superposition. Superposition. 叠加 which means that if we have x1 and x2 to be the input, then f of x1 of t plus x2 of t equals f of x1t plus f of x2t. So this is called superposition. So if you just add the input signal together and then go through this function, it should be equals to the two functions go through the function individually, and then we add the output together. So it feels like you can just distribute, but actually it is not distribution. It is so-called the superposition. And the other one is so-called the multiplication or scaling, something like that. Multiplication, which means that if x is x1 is a function, is an input function, then we can multiply it by arbitrary constant, arbitrary number, and then we can just move this one out of the function. Then it is still correct. It feels like it is quite trivial, but actually in the real world, it's not actually the same. For example, if you just go to the supermarket to buy Coca-Cola, if you just buy a tin, then it might cost you just say 3 Macau per ticket for 1 tin of Coke. Coke. But suppose you buy a pack of Coke with 16 of Coke, then it may just cost you just say 17.5. So this is not linear. This is not linear. If you just buy 16 of Coke independently, then it should of course cost you 18 Macapaticus. But if you just buy a pack of 16, then it may be a bit cheaper. Okay. So linear is important because for linear system, the theory will be easy. In bachelor study, most of the theory involve the linear system, at least in ECE. But yeah, for some non-linear system, then it might be quite difficult, just like the semiconductor physics. Okay, so yes, so far we know what is linear differential equation, but for the linear differential equation itself, it is not easy enough to solve. At least for arbitrary linear differential equation, we may not be able to solve. So there is one specific type of linear ODE which is easy to solve. We have a systematic way to solve. Is that the constant coefficient linear ODE? So just now, for the linear equation, all the coefficients are function of the independent variable. So it is not a constant. It is not a constant because it is function of time. But this type of ODE, linear ODE, is called the constant coefficient ODE. Means that A0 up to AN are all constant. So this type of ODE is easy to solve. It's easy to solve. So it can be written like this, and then this type is easy to solve with a systematic procedure. Okay, so yeah. So here is the summary of the procedure. So the first step for solving the constant coefficient ODE is that. So of course the first step we have the ODE, we have the constant coefficient ODE, and then we should solve the homogeneous solution, or maybe we can call it complementary solution. So it depends. Different textbook might have different names, but I just let you know. We may call it homogeneous solution, or we may call it complementary solution. But here I just use XC. C is the short form for the complementary. So XC of t is the homogeneous solution. And actually, to solve the homogeneous solution, we need to let g of t to be 0. We need to let g of t to be 0. So this is the first step. We can first try to solve this one, and then we can try to find particular solution regarding to the g of t. But for solving the particular solution, actually we cannot solve it for arbitrary g of t, but for some specific type of g of t, we should be able to guess what is the form of the solution, and then we can try to find the coefficient. And actually, this type of function is already quite enough in engineering problem. For example, it already consists of an exponential function, sinusoidal function, and then a polynomial function, and then maybe just combination of them, just multiply 2 of them together, or maybe just multiply 3 of them together. It almost cover all the useful sine or cosine, almost all the useful function for g of t. Because just say for tangent, we do not know how to guess the particular solution, but actually tangent is a function something like this. It will go to infinity, but in the real world we cannot we seldom want to make things go to infinity. But we don't really like this function. Although in trigonometry theory, we need to learn the tangent function to make things complete. And so this is the first step to find the homogeneous solution, and the second step is to find the particular solution. We should memorize how to guess the particular solution, but yeah, it is quite trivial. And the first step is the third step is to just add the homogeneous solution and the particular solution together, and then we'll get the complete solution. And for some of the problem, if we know the initial condition, then we can just find the coefficient of the homogeneous solution, so that make it unique. So finally, we should use the initial value to determine the unknown coefficient in xc of t. For some of the problem, we may not have the initial value, then this solution will be arbitrary many. There will be arbitrary constant in this term, but it'll be fine. So to tell why it will be the case, I can simply explain it like, so for the suppose we have the ODE like this. We have x up to x to the nth equals g of t, something like that. So for the first step, we would like to find f of, just say, or maybe I just call it f of x for simplicity. So if we just find xc of t to be the solution of this equation, which means that we get this equation, and suppose it is linear, then in that case, f times alpha xc of t should also be 0, because we can just multiply alpha on both sides. So on the right side, alpha times 0 is 0. And then if it's alpha times this one, if it is linear, then alpha can be put inside. So at this time, you can already see that there are infinite many functions satisfying this equation. Because if xc of t is a solution, then if you multiply by an arbitrary number, then all these function will still be the solution. And then for the second step, we try to find the particular solution. For the g of t. Then finally, we can just add this equation 1 and this equation 2 together. So it will just like alpha xc of t plus f of xp of t to be, on the right side is 0 plus g of t, which is nothing but g of t. Okay, on the left side, we also know that it is linear, so it should satisfy the superposition property, which means that f of alpha xc of t plus xp of t should be g of t, which means that this function, this whole complete solution should be the solution to this f of x equals g of t, something like that. So this is the first step. So that's why we need this procedure. Okay, so let me talk about this one. So for the first step is to solve the homogeneous solution, the homogeneous solution or the homogeneous equation, which means that if we just let g of t to be 0, or maybe you can just remove the g of t. So the right side is 0, and this one is called the homogeneous equation. And then, so this is the nth order. In this case, we just consider the second order. If it is even higher, then the procedure will be similar, but Yeah, for at least for second order, you know how to solve the the quadratic equation. So we just pick second order to be the example. So for example, if we need to solve this one, just say a times the second derivative of x plus b times the first derivative of x plus c times x equals 0. So this is the second order constant coefficient ODE and the homogeneous equation of it. Okay, so here we try to guess x of t to be the exponential function of time. But here we try to put in a variable here, s here, so that we try to find some value of s, so that this one will satisfy this so-called constant coefficient ODE, the homogeneous equation. You may ask why we would like to assume this function, but the reason is that it works. If you just assume other function, it don't work. So we just assume the function to this homogeneous equation like this. So we try to put in it here, and here. So for the second derivative, so for the exponential function, the second derivative of it is itself, but we need to consider the chain rule. So for the chain rule of this one, we have second derivative, so we have s squared coming out. So we have a times s squared exponential to st, and then this one, the first derivative is itself multiplied by s. So we have s times exponential to st, and then times b for the second term. Third term is just this function multiplied by c. And we can clearly see that exponential to s of t is not 0 for any values. So we can just cancel them. Or maybe you can just divide it on both sides. So that finally we just come out with this so-called auxiliary equation, or we can also call it the characteristic equation. 特征方程. Okay, so this is so-called the characteristic equation. So comparing with this one to this one, you can feel like for the original function, you just exchange it to 1. So for x, you just change it to 1. For the first derivative, you just change it to s. For the second derivative, you just change it to s squared, so on and so forth. Then you can just come up with this characteristic equation without going through this process, because yeah, all the case will be like that. So you just need to remember this one. So you can just change it, this one to 1, this one to s, so on and so forth. But of course, if you can remember this one, you'll be okay. Because maybe you will learn the Laplace transform or Fourier transform later. And actually, that's why we can guess the correct solution. Actually, the Laplace transform or the Fourier transform can solve this kind of linear equation in another way. But yeah. But up till now, you do not learn them yet. So we can just use some fundamental mathematics to go through this process from the homogeneous equation to the characteristic equation. Okay. So let's have a 10 minutes break.